In the beginning was the Big Bang. We are told that 13 to 20 billion years ago, everything that makes up the universe as we know it was spontaneously created out of nothing through an unimaginably violent explosion. But did it really happen as we are told? A growing number of astronomers doubt it and are showing why. This is their story, the story of the universe.
The observational aspects of trying to understand the universe, I think it's reasonable to start about 100 years ago. And about 100 years ago, almost everybody in astronomy, without question, assumed that the whole of the universe was what you could see in the Milky Way. Nobody felt that the universe was any bigger than the stars that you see in the sky, associated with our own local Milky Way. And that was the situation certainly around 1905, times like that. They're well-known people who propounded these ideas. 10 years later, Einstein first proposed his general theory of relativity. Now, when Einstein proposed this, it's a theory of gravity, which means that it's a theory which should represent the whole of the universe, because it's gravitational forces that are controlling the universe. Well, Einstein made this theory around 1915, and he immediately wanted to try and use this theory to explain the universe as it then was, the so-called Milky Way system. But of course, the idea of this was that it was a static system. That is, it wasn't contracting or expanding, it was a static system. And Einstein found that his equations did not allow for a static universe unless he inserted a certain constant in the mathematics, which became known as the cosmological constant. But what happened in the early 1920s was that a very clever Russian called Friedman in 1922 found solutions to Einstein's equations which allow the universe to either expand or contract. Now that was done in the Soviet Union soon after the revolution, and nobody in the West knew about this, I think. But in 1927, a Belgian priest, the Abbé Lemaitre, as he later became, also discovered these solutions. And he went to England, and his work was publicized in Cambridge and elsewhere, and the famous English astronomer Sir Arthur Eddington and others got to know about this, and they immediately began to say, how can this apply to the current universe? Well, in the same period, in 1929, Hubble made what I still believe was the most important discovery in extragalactic astronomy in the last century, or the last century but one. He showed that if you look at the spiral nebulae, the faint spiral nebulae, the shifts in their spectra are proportional to their apparent brightnesses. And this led very soon to the idea that this fitted very well with the expanding universe, and that indeed this is the kind of universe we lived in, that what we were looking at are galaxies, Milky Ways, further and further away from us, and the further away from us, the larger the redshifts, and if that's interpreted in the way that most people would interpret it, this means that they are moving away faster and faster. So this was the original idea. By the 1930s, the front page of the New York Times said, we live in an expanding universe.
When Hubble made his great discovery, it was for galaxies like our own Milky Way galaxy, and they all followed the same rule. that the fainter they are, the larger their redshift. In other words, the faster they are moving away from us. This is known as the Hubble law and directly led to the expanding universe theories. But in the 1960s, there was a new discovery, the quasi-stellar objects, often referred to as quasars. They appear as star-like points on the sky, frequently blue in color, and they have very, very large redshifts, implying that they are at huge distances from the Earth, at the very boundaries of the observable universe. Some astronomers soon found that a vast number of these strange new objects populated the regions around spiral galaxies, and were not only observable with radio telescopes, but were optical and X-ray sources as well. There were two properties of the quasars that were difficult for astronomers to understand using the expanding universe theory. The first was that if one plotted their apparent brightness against their redshifts, as one does for galaxies, one gets an unexpected scatter on the diagram, instead of the smooth curve made by the same plot done for galaxies. This seems to indicate that the quasars do not follow the Hubble law as do most other objects, and that there is no direct indication that they are actually at their proposed redshift distances. In fact, it is argued that if Hubble had first been given the plots for quasars, he and other astronomers would never have concluded that the universe was expanding. The second property was that quasars are very small, compact objects, sometimes only a light year across. So if quasars are really at their extreme redshift distances, they must then be the brightest and most energetic objects known to astronomers. So energetic, in fact, that untestable, almost metaphysical mechanisms must be applied to explain the phenomena. On the other hand, when placed at their observed distances, that is, in the neighborhood of nearby galaxies, their brightness and energies become normal, and no special mechanisms need to be evoked. This problem has led many astronomers to abandon the idea that all redshifts are due to their speed of recession away from the Earth. And if this is true, then there is no need for an expanding universe, and the Big Bang never happened. The questions arise. Is there a connection between certain types of galaxies and the quasar? Are quasars ejected from galaxies, and in fact proto-galaxies themselves? Is there some other astrophysical process which can explain the redshift discrepancies? One of the world's most controversial experts on the structure and morphology of quasars, Halton Arp, has for 35 years proposed just such an idea. For the heresy of opposing orthodox interpretations of the redshift problem, Arp has had to pay a heavy price, the same price paid by many a scientist with new and innovative ideas. Dr. Arp was forced to resign from his permanent position at the Carnegie Institute of Washington Observatories after the Caltech head of the Telescope Allocation Committee threatened him by saying, unless he changed his line of research, they would take away his telescope time. Due to this fact and his ongoing struggle against the established paradigms, Arp is often referred to as the modern Galileo.
I remember when I sent the paper into, the first paper into Astrophysical Journal on the nature of companion galaxies, and I had a lot of them on the ends of spiral arms, so I was sure that they were connected, and I showed that they were systematically redshifted. I sent that in with naive, great expectations that people would be terribly interested and impressed on this. And the editor of the Astrophysical Journal at that time was Subramanian Chandrasekhar, who had a fantastic reputation as a master theoretician and also quite an incomprehensible theoretician, and a tremendously powerful figure in the field, and editor of the Astrophysical Journal, which is probably the most powerful position in the field. And he chose not to, in his wisdom and judicial fairness, chose not to send it to a referee, but he just wrote across the paper, "This exceeds my imagination," and he sent it back to the director of my institute, Horace Babcock, with the obvious implication, you've got to do something about this staff member of yours who's doing these very bad things. And so Horace called me down in the office one day after this, and I walked in his office, into the director's office, and I saw this paper lying in front of him with Chandrasekhar's scroll across it. And Horace looked at me and said, "Well," he said, "this is just too much, and you're going to have to start looking for another job." And so all I could say to him was, "Well, if you send me that in writing, please send me in writing." And I was waiting in great trepidation for weeks and months to get something in writing, and I finally never did, so I realized that he decided to give me another chance, so to speak. So that was fairly early in the game, and then some years went by, and there was the competition for time, particularly on the 200-inch telescope, was getting more and more heated, and people were saying, "Well, we can't continue to give time to this obviously incorrect and embarrassing research that ARP does." So finally they sent a letter to me from the allocation committee, including a number of the younger members of my institute, saying that unless I changed my line of research, that they would have to take away my telescope time. At that point, I considered the situation very carefully, and I figured that the evidence, although a lot more evidence could be gathered and has since been gathered since then, the important thing was not the evidence, because if it was true, it would come out someday. The important thing was the principle of scientific investigation, whether scientists could follow new lines of investigation and follow up on evidence which apparently contradicted the current theorems and the current paradigms. And I also felt that regardless of what happened to me personally, that this was the important issue, and that I had no choice but to resign on the point of this issue, so that if it developed, which I thought it would, that my line of investigation was correct, that people then in the future would say, okay, this was the wrong thing to do, and in the future we're going to have to see that this kind of thing doesn't happen again.
The observers come in now with the belief that we live in a Big Bang universe, and therefore all of their ways of understanding things are tailored to that. And they don't come in with the possibility that our alternative, or any other for that matter, is right, and really do it in an open-minded way. And of course what goes along with that is that observers who would like to test this way find it very hard to get observing time and so on. I mean, this relates to the whole issue of whether the complete lack of balance in the way the observational programs and the funding are conducted. There's no question about that. I don't think that anybody would argue about it.
I've always said that the cause of the troubles is the American graduate school. You get one person who then lectures to his students in graduate class, and because you have a system, you see, when we had graduated first degree, we were independent. We could thumb our noses at the professor. And in fact, the best way to get ahead was to do something that the older people didn't agree with. To be right. That was the way to do it. And but in the graduate school, you all have to learn what you're taught, what the professors are teaching you. And then those people go out and get jobs, and they have another graduate, their own graduate school, and it just tier after tier. You get a few places like Caltech or like Harvard, and they set the fashion for every place.
I think there's a problem with graduate education. I think
Imagine if every puzzle on Earth was solved. Every why that we have pondered, but could not answer for all our trying, be mastered. Imagine if we all, God's ways, could clearly understand. Will this be reality, or is it just myth? Our thinking is like the streaming colored lights, flames flickering across the dark northern night. It was dark before we started thinking, and it will be dark again if we stop. Some claim that most questions in nature have been answered. Others think that we have only just begun asking. This is their story, the story of the universe.
plasmas are found virtually everywhere. They're found in solid state matters at very low temperatures. A flame of a match, a fluorescent light is a plasma. Fire in your fireplace is a plasma. The aurora obviously is a plasma. The sun and all of the stars are a plasma. Lightning is a plasma. In fact, 99.999%, as Alfvén used to say, of all observable matter in the universe is matter in the plasma state.
A plasma is an ionized gas. It means a gas consisting of charged particles rather than neutral particles, which is the constituents of a normal gas. The charged particles are electrons and atoms that lack electrons. So it consists of negative and positive particles that interact with each other by means of electric and magnetic fields.
The term plasma, as applied to electromagnetics, was first coined in 1923 by the Nobel laureate Irving Langmuir to describe the experiments that he was doing at the time. Basically, plasma consists of charged particles, the electrons and the ions or protons that we know in nature. It can also include charged dust. And in Irving Langmuir's experiments with the charged particles, he noted that they acted almost in a lifelike manner. They tended to develop cells. They acted very much in a way that indicated that they might somehow be related to life. And for that reason, he borrowed the term plasma from the blood plasma.
A plasma is like a society of individuals where all the individuals are interacting with each other through complex interactions like media, newspapers, television, and so on. And the normal gas is like a society where the individuals simply basically don't interact or interact at very short distances, very local communities.
The first effort to understand how plasma functions in the universe, to understand the plasma universe, was Christian Birkeland, who at the end of the 19th century wanted to understand what is the nature of the aurora.
Birkeland became interested in the aurora at the beginning of the 1890s, and it was, without a doubt, due to his work with cathode ray tubes. Cathode ray tube is a vacuum chamber with an electric current, so when the air pressure gets low enough, current passes through. In Birkeland's day, they didn't know there was a current because electrons hadn't been discovered yet. But in any case, Birkeland found an analogy between the cathode ray tubes and what he had observed on the sun.
We're studying, for the first time, the nature of electrons. And you had, for example, the development of the cathode ray tube. The cathode ray tube we're familiar with. This is what powers our computers and our television screens. You have electrons accelerated, smashing into phosphorescent atoms in the screen and producing light.
Already before this time, Birkeland believed that cathode rays came from the sunspots and struck the Earth, creating the auroral displays. This connection between the sun and Earth had been around a while, because scientists were aware that when powerful solar explosions were observed, for example, like the one in 1859, that a powerful magnetic storm was also observed on Earth afterward. And because of this, Birkeland concluded that the sun and Earth were connected, and that cathode rays were the cause, and also that there must have been an electric current between the sun and Earth that sent the rays.
Some people have said that science is a method for asking questions of nature. And if that's true, then we can say the Big Bang supporters are people who won't take no for an answer.
Over the last 2 or 3 decades, the Big Bang theory has become increasingly more and more speculative. One expects from a scientific theory definite predictions which can be tested by observations. If the observations disprove the predictions, the theory is supposed to be disproved and it should be modified or abandoned.
In science, we work from observation, from empirical observation that starts in the here and now and works outwards and backwards. The Big Bang starts from mathematical formulas, deductions that start from the beginning of the universe and to try and predict it forward. This is the same mathematical approach, mathematical deductive approach, that led 2,000 years ago to the development of the Ptolemaic universe. The universe, of course, which was Earth-centered, with the planets going around the Earth, with the stars in a crystalline sphere. What these theories have in common is that they try and derive what should be the universe, based on what perfect principles we can develop, what God should have made the universe to look like. And then they try to fit the universe into that perfect framework.
However, what has happened over the years is that whenever observations have come up which don't agree with the predictions of the Big Bang theory, the theory adds an extra assumption which is not at all tested, which is not at all resting on conventional physics, and simply assumes that that must be true.
The problem with that is that develops myth, not science. It develops a religious faith in which nothing in the real world, in the observable world, can contradict the faith in this structure, in the Big Bang. This undermines the entire scientific enterprise. The reason science has been valuable to human beings is because it allows us to predict nature in such a way as we can use nature in a predictable fashion in technology. To abandon this approach, which has served us so well, and to go to the idea that we can deduce, we can read the mind of God, as Stephen Hawking says, and deduce from perfect mathematical principles what the universe must be, is to abandon the scientific method.
In standard Big Bang cosmology, you have what I call a series of epicycles. The Greeks used to have epicycles, which are known as circles whose centers move on other circles, whose centers move on other circles, in order that they could correctly describe the position of a planet at any given time. They found that in some cases they had to introduce many circles before they could get anywhere near the reality. These epicycles are the assumptions that have been put in ad hoc into the theory from time to time.
It's very small matter. What was dark matter? Dark matter was some matter that we don't understand, we don't know what it's about, we haven't observed it, but it isn't ordinary matter, so it doesn't enter into our equations about the light elements, and we can't see it as stars. But dark matter is 90 or 99% of the mass of the universe. This is what we call in science a fudge factor. When your equations don't work out, you just write in this little plus something. Well, in this case, this was a humongous fudge factor because it was 90 or 99% of the universe.
And you have to not only postulate that this matter has to exist, but it has to exist in quantities much greater than the amount you see of ordinary matter.
And I should emphasize that people have looked for dark matter. People have looked for dark matter since it was proposed 20 years ago. Axions, WIMPs, little particles that are supposed to be floating around in space that we should, in theory, be able to observe as they pass through the Earth. Dozens of experiments have looked for these particles. Not one has been found. Again, this should be a contradiction. The way science works, you make a prediction, observation contradicts it, the theory should be rejected. But that hasn't happened. And the epicycles don't end. There's a problem with dark matter, even theoretically. Even though we can't observe it, there's still a problem with it, which is dark matter slows down the expansion of the universe. So the length of time that the universe has existed, the length of time since the Big Bang, should be shorter than what's indicated just by linear expansion. Well, the problem is it's too short. The prediction of the cold dark matter theory is that the universe should be about 8 billion years old. Well, that's a big problem. We can determine the age of stars in our own galaxy, in the oldest globular clusters, both based on very well confirmed theories of the nuclear evolution of stars and spectroscopic observation. And the stars in our galaxy are 13 or 14 billion years old. So it's very embarrassing to have 14 billion year old stars in an 8 billion year old universe.
In addition, they went into dark energy. Now, why did dark energy come in? Because if you take the present value of the cosmological constant and the cosmological constant which came out of inflation, you find that they are not the same. Not only they are the same, but you have to find that the difference lies in something like 108 orders of magnitude. Now, can you imagine a physical theory getting the answers wrong by a factor 10 to the power 108? Yet, the Big Bang cosmologists very coolly accept this and simply put in another epicycle by saying that there is a dark energy which has changed over the time by this factor. So we have to accept that.
Dark energy is some force, again, unknown on Earth, unpredicted by any theory that we have validation of here on Earth, that causes an acceleration of the expansion of the universe. So as the universe is accelerating, and it's older than appears on the basis of the dark matter theory, and it's 15 billion years old. So we solve the problem of the age of the universe by hypothesizing yet a third completely ad hoc epicycle dark energy. So now we have a universe which is 70% dark energy, 28% dark matter, and only 2% matter that we can observe through our telescopes and here on Earth. Epicycle is being piled onto epicycle. And in the process, what we call the predictive power of the theory is fading away to nothing. One of the most destructive features of the methodology of the Big Bang is that it conveys the idea that only experts can understand the universe. Only people versed in extremely complicated mathematics can understand the universe. That if dark matter, dark energy appear to be incomprehensible or even nonsensical, it's because you don't understand the mathematics of these complex equations. This is, of course, the argument of the emperor's new clothes. If you can't see the emperor's new clothes, then you must be either stupid or incompetent.
So this goes on, and we can find that the old Greek tradition of epicycles, which was even adopted by Copernicus and has been continuing in standard Big Bang cosmology. If we go by the history, the Keplerian orbits, which were elliptical orbits, very cleanly and neatly resolved the problem of planets. And the circles upon circles idea had ultimately to crumble down. Now, in the same way, I suspect that the Big Bang theory will collapse under its own weight of assumptions, and a more neat theory, neat interpretation of the universe will emerge.
Does this mean that the age of the universe is not what Big Bang theorists have implied? Could the universe be eternal after all? How much are cosmologists really able to know?
We are now in a stage which can be called a plasma universe. And we are simply not privileged to know what stage the plasma universe evolved from. We do not have privilege to that information. We do not know. We will never know. And this is one major difference between the plasma universe cosmology and the Big Bang cosmology that claims to be closing in on the final answer.
The universe described by plasma cosmology is quite different. Here we are talking about a universe with no beginning and no end, an infinite universe, continuously evolving, an evolution that is continuously increasing at an ever rapid pace. It is a universe in which there is a coherence between what we can understand in the here and now on Earth and what we can understand in the rest of the universe. A universe in which there is no real limit to our ability to understand more new phenomena. And a universe in which we can apply what we learn in the universe in present-day technology.
The basic difference between plasma and all other forms of matter, that is solid, liquids, and gases, is that a plasma produces electromagnetic radiation and also tends to filament. So that we would expect in a simulation, which is what we see, in an experiment, which is what we see, we would expect to see throughout the cosmos a filamentary structure that is a spaghetti of currents intertwining the cosmos.
We can use plasma theory derived from experiments in the laboratory, from the basic concepts of plasma instabilities, from Maxwell's equations, and from the well-known laws of gravitation, to describe and predict how the structure of the universe came into being and what that structure is. So the key question is, how could this structure come into existence? Now, in the Big Bang theory, the universe starts out extremely homogeneous, very smooth.
This was in direct contradiction to the plasma universe that insisted that the universe overall must be filamentary.
But what we have today is extremely clumpy matter. When I talk about these huge voids, the structure of voids, the matter inside the voids is less than 10%, perhaps less than a few percent as dense as the average. And the matter in the walls of these voids, where these filaments of superclusters of galaxies are located, is 10 or 20 times the average. So you have extreme clumpiness. Now, what's the problem for the Big Bang to explain this? There's a huge problem. There is not enough time since the Big Bang to form these structures. These structures are older, much older than the time hypothesized since the Big Bang.
Now, again, in interpreting the observational information, we can again go to the laboratory, which we are privileged to diagnose in any number of ways, in any number of directions, and run any number of experiments, which you can't do with the universe. But we also turn to the supercomputer simulations. Now, what a simulation does is that it allows you to model the plasma, regardless of size, put in the rather few basic initial equations, and then follow the simulation through its various nonlinear stages and the different morphologies or shapes that the plasma will take.
In Tony Peratt's simulations, as the current spirals into the center of the galaxy, turns around and moves out along the axis of the galaxy. In that central area where the current is extremely concentrated, there seemed again the potential for violent events. And Alfvén and Peratt raised the question, couldn't this be a way of explaining the extremely violent events that occur in the center of galaxies that are known as quasars, in which huge amounts of energy are released in what, by astronomical terms, is a relatively small amount of time. That is, millions of years compared with the billions of years galaxies exist.
Initially, the time frames shown represent 1 billion years or so, but now we're going to carry it out for 10 billion years to see what happens to these double radio galaxies, or quasars, as the two filaments have evolved into. And you'll see that the tails start to elongate, and fairly soon you're going to start to see a spiral structure. And as we get closer to 10 billion years, the end of the movie, you will see that we have formed the shape, the morphology, the shape of a spiral galaxy.
Now, Alfvén developed a number of concepts that were critical to the whole understanding of the plasma universe. First of all was the basic concept of scale invariance in plasmas. That means there are certain phenomena in plasmas that don't change regardless of whether you're dealing with a laboratory scale of centimeters or a solar system scale of millions of kilometers or a galactic scale of hundreds of thousands of light years. What that meant was that time scales the same way as distance does. So not only does this mean that the phenomena of the cosmos can be studied in the laboratory, but because of time compression, the phenomena of the cosmos are essentially transient phenomena. It's funny to think of a galaxy lasting billions of years as a transient phenomenon, but it's analogous to events in the laboratory that last only millions of seconds. Another way of putting it, the plasma universe is extremely dynamic.
It's not going to be hypothesis. We've moved further than hypothesis. We've definitely gone into the second lake, the analysis, and we're well towards the third lake. Now, we haven't reached the third lake, of course, and perhaps, well, you can't with the universe because you can't experiment with the universe itself. Now, of course, we, like Alfvén, his idea. Indeed, you can determine what's happening in the universe in an experiment, but as far as producing universes, well, we're not going to do that. So we're going to do the best we can in the laboratory.
The universe that the Big Bang envisions and the universe of plasma cosmology are very different universes, and they have very different implications, and they cohere with very different ideologies of what is happening here on Earth.
The Big Bang theory will collapse under its own weight of assumptions, and a more neat theory, neat interpretation of the universe will emerge.
Again, of the kinds of things I said in 2001, to give you a refresher on the electric universe model that I'm proposing, and then to talk about how that might fit with the kinds of things that have been uncovered by the comparative mythologists in the US, Dwight Cardona, Dave Talbot, Ev Cochran, and others. And it's, of course, just my view, and it seems to make sense to me, but it may not make sense to you, and I'm quite happy to discuss the sense or the nonsense after I've spoken. This slide I used to open the conference presentation in Amsterdam. I tried to gauge the audience's reaction to it. I said, does this send a shiver up your spine when you look at it? Because in this picture, Mars is about 100 times closer to the Earth than its present closest approach at about 15 million miles. The image is superimposed with plenty of lightning and so on at the Kitt Peak Observatory. And of course with that well-known quote. This is the book, or the first book in a series, which is available on our website, thunderbolts.info. And it's the first few chapters of a series. The second in the series will be the electric universe. But this one is a kind of introduction, and it also features some of the work of Tony Peratt, who I'm very pleased to say is in the audience and will be speaking after me. Both David Talbot and myself got our inspiration initially from Immanuel Velikovsky, who threw down the challenge to science of the day by proposing that electromagnetism had a role to play in the dynamics of the solar system. Of course, we all know what happened. It was many years later that I finally came to the big picture view, if you like, that electricity is at the heart of everything. In other words, all matter is made up of charged particles, and that their interactions at all scales is what gives the complexity and the wonders of the universe that we observe. The idea is, and this is rather heretical, this is supposed to represent a hydrogen atom with the nucleus appropriately placed here, and the electron shown to have structure. In other words, an electron is not a fundamental particle, it is a composite particle made up of subunits of charge. Now this idea came from Ralph Sansbury, who has been to some of our meetings and who I'd like to see along again. One of the requirements of this model is that these electrical particles are able to communicate at near infinite speed. Otherwise you cannot form stable systems of particles. You cannot form stable electrons, protons, neutrons. In other words, we wouldn't have the universe we see today. But of course, if you talk about communication at near infinite speed, you then have to worry about Einstein and the things that are believed as a result of his work. And in fact, you have to give Einstein's theories or his interpretations of the mathematics a miss and look at it all again. Of course, this kind of communication between these subparticles within normal matter has meaning for biology too, because it means that every complex system of atoms will have a kind of a resonance about them which is communicated to nearby and even distant molecules of the same configuration. So in other words, you start to see how the mind-body connection might work. And you get the impression also that the idea that nerves carry the signals around the body about what is going on in the environment is totally inadequate. I mean, nerve signals travel at speeds measured in meters a second. If we have all of the mind and the body connected at near infinite speed, we begin to understand how the amazing complexity of consciousness and so on may work. When we go from that level, we go up to space and we're looking at the interaction of charged particles in plasma. And this, of course, is Tony's area of expertise, and we'll hear about some of the amazing formations that plasma can adopt. So that's a very quick vision of how it works at the most fundamental level. In the big picture approach, of course, there are many aspects which have to be plugged in and fitted like pieces of a jigsaw puzzle. So it embraces plasma cosmology, because I think that's the most complete description of what's going on in space. It embraces Halton Arp's discovery of the birth of galaxies in the form of quasars from the centres of active galaxies. This electrical model of matter, the structure of matter, also explains gravity and magnetism, because if you have these charged particles in an electric field, they will be distorted and form tiny electric dipoles. One form of the dipole at the atomic level creates magnetism. Gravity is the distortion of the subatomic particles themselves, the electron, the proton, the neutron. That explains why gravity is such a weak force, because the distortion of these subatomic particles is absolutely minuscule. Quantum weirdness now has an explanation. Instead of using probabilistic mathematics to describe what goes on in the world, and I'm reminded of Douglas Adams with his infinite improbability drive. You know, with that kind of mathematics and underneath your physics, it means that almost anything can be said and explained away as being, well, you know, there's a finite probability that it will occur. And I think that's hopeless physics. If you give this substructure to matter, you then have the possibility of explaining quantum effects, that is, jumps from one energy level to another, as simply jumps from one resonance state to another. Of course, that discards certain things along the way. If you take this view, genetic determinism goes away because we're in contact with something outside, beyond the body. It also, the plasma physics view also shows us that we have a dramatic history of the Earth. It's nothing like what we believed before. And it seems to be offering a coherent big picture, because all of the discoveries that keep pouring in almost on a daily and a weekly basis have no trouble in fitting this model, as far as I can see. And I'm also encouraged by others who look at this theory and then look at the news reports and come to me and say, well, you know, it makes sense. We come to plasma. On the screen there you see a simple plasma ball demonstration, which you've seen in novelty shops and museums. And you can see there that the electric discharge in the plasma takes a filamentary form. And if you look at the ends of the filaments, you can also see that they seem to be twisted pairs of filaments. And this is important. Well, plasma physics and plasma cosmology, in my view, are extremely important, because plasma comprises almost 100% of the visible universe. Now, we live at the bottom of an ocean of atmosphere where we don't have to deal with plasma on a daily basis, although occasionally you get an electrostatic shock when you get out of the car and grab the handle and that kind of thing. But in space, the charged particles do tend to be separate and form this plasma, which then, unlike any solid, liquid or gas, which we're familiar with, it is conductive like a metal. It forms these filaments and bubbles and sheaths and has a magnetic field associated with it, generally if it's moving. Also, it can be recognised in space, even though it may be invisible to the visible spectrum telescopes. It produces prodigious electromagnetic radiation over large parts of the spectrum, which means that it can be detected by radio telescopes and, in intense examples, by X-ray and gamma-ray telescopes. You can almost see why we've gotten to this predicament of not recognising the importance of plasma effects in space by the fact that we've grown up in this electrically, effectively neutral environment. But that's no reason to continue this way. Once we discovered plasma in space, then we should have been looking at electrical effects in plasma to help explain strange objects like this, the centre of the Crab Nebula. Now that has all of the characteristics of a homopolar or a Faraday disk motor or generator. In other words, you have current moving along the axis and also in the plane of this disk. And we see this formation almost everywhere we look. Now, I sat in on the lectures. I didn't do the exam because I figured it was a waste of my time. But I sat through all of the lectures of the postgraduate astrophysics course at University of London. And at the end of the semester where we did plasma physics, I went to the lecturer and said, when do we cover the subject of electric discharges in plasma? And he said, we don't do that. I said to him, I think you're missing one of the most important aspects of cosmology. And he sort of turned on his heel and who are you? So astrophysicists aren't taught this subject. It's really in the realm of electrical engineering and the extreme end of electrical engineering, I think, as Tony would say. But it means that, in my view, the cosmology of the future will be open to the backyard tinkerer, because you can actually get out in the garage, and provided you do a little bit of electrical engineering, you can wire up high energy devices to create discharges and see what happens. You can use an arc welder to scar surfaces and then have a look at it under the microscope at what goes on, and then relate that to things that are being seen in deep space. Astronomers are not doing this. I talked about the twin filament, or filament pairs, that Birkeland currents, named after one of the pioneers of the electrical nature of the Earth and the solar system. And electricity tends to flow through plasma along magnetic field lines. So you're able to trace magnetic fields in space wherever the plasma is radiating, and it can be seen. So this double helix kind of arrangement can be seen in ejection of material from the sun, for instance. Of course, the astronomers say that it's magnetic effects that cause that. It's nothing to do with electric discharge. I was at a meeting of the National University where the director of the School of Astrophysics admitted that when we don't understand something, we blame it on magnetism. They were her exact words. As if magnetism did by magic. Now, we've already discovered these planetary Birkeland currents. Back in the 80s, there was an article in New Scientist which was headed, "Soho catches Venus by the tail." Now, this is a distance of 45 million kilometres between Venus and the Earth, and the spacecraft here, Soho, discovered these strange stringy things. And there was no explanation for that, because it was felt that plasma from the tail of Venus would just blow and disperse like smoke in a wind. Instead of that, they found that it was kept into these very well collimated stringy things. And that's exactly what you'd expect of an electric current flowing from Venus away from the sun and impinging on the Earth. And this is important in how we achieve stability. I'll talk about that later. This is a very simple device which Tony knows quite a bit about. It's called the plasma gun, and all it is two cylinders of metal with an insulator between and a source of high energy, electrical energy. What you do is you fill a room with capacitors, charge them up, and then you have a special switch which you then throw, and the discharge begins at this end of these two cylinders and moves down this way. That's what this represents, the front of the discharge. When it gets to the end, it sort of balloons out of the end and then collapses back into the centre of the inner tube and forms a tiny donut. And all of the energy stored in that huge array of capacitors is concentrated in a little donut about 0.5 millimetre across. Now, the electrons in that eventually get tangled up and the thing decays, but as it decays, it fires this intense beam of X-rays and particles along the axis. Now, this is a way of showing what happens when you concentrate electrical energy from a dispersed source down to a compact source. And in the universe today, we see repeatedly evidence of very compact sources of high energy radiation. And it's blamed on things like black holes, neutron stars, and strange things going on in the centres of active galaxies. All it is a concentration of electrical energy. This is looking down the barrel of the plasma gun, showing the Birkeland pair filaments radiating out from between the two electrodes. And this is the plasmoid where the energy is collapsed in. It's only 0.5 millimetre across in this particular experiment. We look out into space, and this is looking down the barrel of a planetary nebula. Now, Charles Bruce, the English electrical engineer and fellow of the Royal Astronomical Society, picked these as being an electric discharge phenomenon back in the 60s, I think it was, or maybe even earlier. Here we have a very good comparison of this plasma gun effect with something that's seen in space on a much grander scale. Now here's a stellar scale plasma gun, and can you imagine a jet like that extending from our star to 3 times the distance of Alpha Centauri? But this is what you've got. I've been to many meetings of the astrophysics department at the National University where they're spending an enormous amount of time and money trying to model these jets and explain how they punch their way out and still maintain that very fine collimation. And they haven't succeeded. But this is just a natural form of this plasma gun discharge effect.
The links to both of these videos will be accessible in the description. Strongly recommend watching the full videos to get the full amount of information that's available on this. I'm just touching on it. Follow up and it will be worth it. Thanks for watching.